In this video, you'll see how to create an always on and always off bit using ladder logic. Begin by selecting the blocks folder. A common place to create an always on and always off bit is in OB1. So let's open OB1. Right-click the last network and insert a new network. Add a normally open contact and a coil. Select the network line in front of the open contact and branch down. Add a normally closed contact and close the branch. Select the first contact. It is commonplace to use a memory bit that ends in 0.1 for an always on bit. So let's add M0.1. Type M0.1 over the closed contact also, and over the coil. If M0.1 is true or false, the coil will be true, so the bit will be always on. Let's add a symbol name. Right-click one of the addresses. Choose Edit Symbols. Select the symbol field, and let's add the name always_on. Click OK. Let's add another network. Select the network line and add a normally open contact, a normally closed contact, and a coil. It is common to use a memory bit that ends in 0.0 for an always off bit. Select the open contact and we'll enter the address M0.0. Select the closed contact and enter M0.0 and enter M0.0 for the coil. Let's add a symbol name. Right-click one of the addresses. Choose Edit Symbols. Click the symbol field and add the name always_off. Click OK. Let's widen the address field. Select Options. Choose Customize. Select the LAD FBD tab and let's extend the address field width to 18. Press the Enter key. Save the block, download it, and turn monitoring on. Select the network where you want to begin monitoring. Here you can see that M0.1 will always be on and M0.0 will always be off. And that concludes this video. This video shows how to add some simple Boolean logic elements to an existing Step 7 ladder logic program. From your SIMATIC project, highlight the blocks folder. Let's open a block. Double-click FC16. Drop down the bit logic folder to see the available Boolean logic commands. Click the network where you want to insert new logic. Click to add a normally open contact from the shortcut bar. Next, we will double-click on a normally closed contact from the bit logic folder to add it to the network. A special note here is that the network or an element on the network must be selected before you can double-click to add logic from the bit logic folder. You will get a message if the network extends beyond the margins of the page. Click OK. Next, let's add a NOT command by using drag and drop. The NOT element is used to invert a signal. If a 0 comes in, a 1 is sent out, and vice versa. So far, you have seen that you can click to add a contact from the shortcut bar, double-click to add an element from the bit logic folder, or drag and drop an element from the bit logic folder. Select the first contact's address field. If the program option automatic symbol selection is turned on, begin typing an address and a drop-down window will show you all available symbols of that data type. This option is set through Options menu, Customize, and View tab. You can see a demonstration for this and other settings on the View tab by watching both videos on Program Editor Options, Customize, View tab, Part 1 and 2. Double-click to choose the symbol T_Bay1. Select the next contact's address field. Begin by typing a T, and double-click to choose the symbol T_Bay2. Next, we will add a branch. Click the network where the branch is to begin. From the shortcut bar, click the down branch. Also from the shortcut bar, click to add a normally open contact. If you want to close a branch around a single element, click the Close Branch button. If you want the branch to extend around several elements, grab the double-headed arrow and drag to the location where you want to close the branch. Click the address field of the new contact. We will begin by typing in A and select always_on from the list. The purpose of this demonstration has been to show how to add some basic Boolean ladder logic to existing ladder logic, not to focus on what the logic does. And that concludes this video. This video shows the difference between the assignment, set, and reset coils in ladder logic. To begin, let's open a block. We will choose FC1. Double-click to open FC1. Drop down the bit logic folder. To begin adding logic, click the network. First, let's add some logic using the shortcut bar. Click the normally open contact button. Now add the assignment coil from the shortcut bar. Let's add a second network. Right-click on Network 1. Choose Insert New Network. For demonstration purposes, this time we will choose some logic from the bit logic folder. With Network 2 highlighted, double-click the normally closed contact. Double-click the set coil. Let's add another network. Right-click on Network 2. Choose Insert Network. With Network 3 highlighted, double-click on the normally open contact. Double-click on the reset coil. Let's address these elements. We will make the first one be input I1.4. Press the Enter key to move the highlight to the next element, in this case, the assignment coil. The assignment coil address will be Q4.7. Press the Enter key. Select the normally closed contact in Network 2. We will assign the address I1.5 and press the Enter key. Type the address to be Q5.7. Select the normally open contact in Network 3. We will make this address I1.6 and press the Enter key. The reset coil will carry the same address as Network 2, Q5.7. The block FC1 needs to be saved and downloaded, which will not be shown. FC1 is already called from Organization Block 1. Now let's monitor the code. The assignment coil follows the logic, or said another way, changes with the logic. If the result of all the logic before the coil is false, the coil will be false. If the result of all the logic before the coil is true, the coil will be true. Input I1.5 is a normally closed contact. Since the actual input is off, the logic going to the set coil is true. Once the set coil goes true, it will remain true until it is reset by a reset coil. The normally closed contact input I1.5 has been turned on, so the logic going to the set coil is false, but notice the set coil remains true. The reset coil agrees with the set coil and is true. Input I1.6 has been turned on, and the result of that logic is true, which resets output Q5.7, and the coil goes false. The set coil agrees with the reset coil and is also false. The result of the logic in Network 2 is true again, therefore the coil is set. When the logic in Network 2 goes true, the coil Q5.7 is set or true. When the logic in Network 3 goes true, the coil is reset or false. If the logic in both networks remains true, then Network 3, the last one scanned, writes the logic to the output coil Q5.7, which will be false. In this demonstration, you have seen that an assignment coil, such as Q4.7, follows the logic. A set coil remains true until it is reset. If the logic to both a set coil and a reset coil is true, Then the last one scanned writes the logic to the output. And that concludes this video.
This video explains the differences between going online with a block and monitoring a block. Here is an offline project with the blocks folder highlighted. Let's open an online blocks folder. Click the Online button. Click the Stack Vertically button. The top window is the online window, and the bottom window is the offline window. Double-click to open the offline block FC16. Notice that the name here does not say Online. Click the glasses to turn on Monitoring. The name at the top of the block adds the word Online after Monitoring is turned on. Also, the @ symbol appears, which indicates monitoring. Click on the Error tab. The statement in the Error tab tells you that the offline block is open. The block's content agrees with the actual online block in the PLC, or we would not be able to monitor it. Double-click FC16 in the online window. The name now says Online, even though monitoring is not turned on. Notice that the @ symbol is also not displayed in the name bar. Click the Error tab again. The note in the Error tab shows that this is the online block, meaning it is the one in the PLC. Turn the monitoring glasses on. Notice that the @ symbol indicating that monitoring is on displays in the name bar again. Close the window. Double-click the offline FC16 block again. Click on the Error tab. The Error tab shows that this is the offline block. Now let's see another way to open the online block. Click the Offline Online toggle button. A message displays asking if you want to close the current block and open its partner with editing capability. This means the offline block will be closed and the online block will be opened and can be edited. Note that the statement in the Error tab now shows that this is the online block. The name bar also shows Online but does not show the @ symbol. Turn monitoring on. The @ symbol displays again when monitoring is turned on. Click to turn the monitoring off. Minimize the window. Currently, the online version of FC16 is open. Let's double-click the offline version of the block. A message displays telling you that another version of the block is open and the block cannot be written to. Therefore, editing is not possible. For demonstration purposes, we will click OK to the message. Open the Window menu. Choose Arrange and Horizontally. Click the Online window to make it the active window. The name bar shows Online with no @ symbol, and the Error tab shows this is the online block. Now click the Offline block to make it the active window. The Error tab at the bottom now shows that this is the offline block. In review, you can look in the Error tab to see if the open block is the Online PLC block or Offline Project block. If the @ symbol displays in the name bar, it means the block is being monitored but does not tell you if it's the online block or offline block. If there is no symbol displayed in the name bar and the block still says online, then you are in the actual online PLC block. And finally, if both the online block and offline block are open simultaneously, editing capability is lost. And that concludes this video.
This video shows several ways to use and several uses for the SIMATIC Program Editor's empty box for ladder logic. Let's open the block FC1 with a double click. Drop down the Move folder. To transfer data from one location to another, you use the Move command. When you know a command's name, you can use the empty box to insert it into the code quickly, without having to locate it in the programming catalog. On the shortcut bar, the empty box is the one with the 2 question marks. With the network highlighted, click the empty box button. Type out the word move and press the enter key. The empty box then becomes the move command. Let's insert another network. Right-click on Network 1 and choose Insert Network. Drop down the Timers folder in the programming catalog. All the standard timers begin with an S followed by an underscore. Let's add a pulse timer by using the empty box. A second way to add an empty box to a network is to right-click on the network and choose Empty Box. Begin typing S_P. The extended pulse and pulse timer come into view. Double-click on the pulse timer. The empty box now becomes a pulse timer. Let's add another network. Drop down the Libraries tab. Drop down Standard Library. Drop down System Function Blocks folder. System Functions, or SFCs, and System Function Blocks, or SFBs, are burned into this CPU's ROM. The empty box will also locate these type blocks. Right-click on Network 3 and insert an empty box. SFB4 is an IEC on-delay timer. In the empty box, type SFB4 and press the enter key. You can use the empty box for programming catalog elements, SFC or SFB calls, and user block calls. The empty box will not find FC or FB library blocks in the other library folders. You have seen how to insert an empty box from the shortcut bar and with the right-click context menu. This is a great tool for inserting program elements quickly if you know their name. Using the empty box for user block calls is demonstrated in the video Methods to Call a Subroutine in Ladder, and that concludes this video.
This video demonstrates several ways to call a subroutine in ladder logic. We'll begin with a program block open and several empty networks. Drop down the FC blocks folder. The first method is to locate the subroutine or block and drag it onto the network. The second method is to first click on the network and double-click on the subroutine. A third method is to right-click on the network and choose Insert Empty Box. Enter the block's type, such as FC followed by the block's number. You may choose to use the name instead, but you must type out the full name exactly as it appears next to the block's number. Another way to select the empty box is click on the network and click the Empty Box button on the shortcut bar. Type FC followed by the block's number and press the Enter key. Drop down the Function Blocks folder. Let's make the subroutine call by dragging a function block to the next empty network. When a function block is called, the data block must be attached for purposes of holding the function block's data. An easy way to create the data block is click on the 3 red question marks. Type DB followed by a number. The editor will not let you reuse a data block number, so you will not accidentally duplicate or overwrite an existing one. You can see what numbers already exist by looking in the S7 blocks folder. Let's assign DB300. If symbol selection is turned on, like it is here, press the Enter key once and press Enter again. The program editor will tell you that data block 300 does not exist and asks if you want to generate it. Choose Yes. The data block has now been created and the function block subroutine call is complete. Drop down the SFC blocks folder. Also drop down the SFB blocks folder. Let's insert another network by clicking the New Network button on the shortcut bar. SFC and SFC blocks are special library blocks that are burned into the CPU's ROM. System functions and system function blocks are simply FCs and FBs that are pre-written and perform a special function. The subroutines reside in the library's Standard Library System Function Blocks folder. When an SFC or SFB has been used once, it will appear in the program editor's SFC or SFB blocks folder, and you do not have to get it from the library a second time. Let's make a call to SFC1 by dragging it onto the network. Let's add another network. Click on the network and double-click SFB0, the IEC count-up counter. This is a system function block, so a data block must be attached. Click the 3 red question marks. Type DB followed by the number and press the Enter key. Press the Enter key again. Choose Yes to generate the data block. And the call is complete. You have seen how to make subroutine calls to FCs, FBs, SFCs, and SFBs. You have also seen that you can make the call by dragging a subroutine onto a network, highlighting the network, and double-clicking on a subroutine, or insert an empty box and type the subroutine's type such as FC followed by the block number, or by typing the block's full name. This concludes the video on methods to call a subroutine in ladder logic. This video demonstrates how to add block titles and comments as well as network titles and comments. Open the FC5 block. First, we will add a block title and some network titles. Click in the block title field. We will add the title Start Motor 1121. Click in the Network 1 title field. We will add the network title On Delay Timer for Cap Energize. Click on the Network 2 title field. We will add the title Start Motor After Cap is Ready. If comment fields are not displayed, click the View menu. Choose Display With and select Comment. Comment fields are now visible. Click to add a block comment. A comment has been copied from a text document. We will paste it here by pressing the Control key plus the V key. We will do the same for Network 1's comment. Click on Network 1's comment field and paste the comment. Click on Network 2's comment field and paste the comment. When you're done adding titles and comments, save the block. This concludes the video on adding block and network titles and comments.
This video demonstrates positive and negative edge detection or one-shots based on result of logic operation, also called RLO. Network 1 has a positive edge pulse coil or positive one-shot. Network 2 has a negative edge coil or negative one-shot. Each pulse coil gets assigned a unique memory bit which tracks the incoming logic and determines when a pulse should be fired through to the coil. Network 3 is used to reset the output set coils for networks 1 and 2. Turn the monitoring glasses on. Memory bit 63.0 keeps track of the result of logic, or RLO, just before the P coil. When the RLO transitions from 0 to 1, a positive edge pulse or one-shot is fired through to the set coil M300.0. This means if I0.0 were true, and I0.1 transitions to true, a positive edge pulse or one-shot is fired, and the set coil M300.0 goes true. Let's reset coil M300.0 with input I1.7. Here input 0.1 is true. If 0.1 is true and I0.0 transitions to true, a positive edge pulse or one-shot is again sent to the coil. So either input can be true, and when the other transitions to true, the result of logic or RLO transitions from 0 to 1, and the positive edge pulse or one-shot is fired. Let's reset the output coil again with I1.7. The negative edge pulse coil fires a pulse or one-shot on the trailing edge when the result of logic changes from 1 to 0, regardless of the order of change. For example, if I1.0 is true, and I1.1 goes true, and then I1.1 goes false, a pulse coil is fired, and the set coil M300.1 goes true. Let's reset the output coil. If both I1.0 and I1.1 are true, and this time I1.0 goes false, the pulse will be fired and the coil M300.1 goes true. So if both inputs are true, then if either one goes false, the pulse is fired. In review, a positive edge pulse coil fires a pulse when the result of logic right before the positive edge coil transitions from 0 to 1, regardless of the order in which the logic goes true. The negative edge pulse coil fires when the result of the logic before the negative edge coil transitions from 1 to 0, regardless of which bit logic goes to 0 first. And that concludes this video. In this video, you'll see the pulse timer and the pulse timer coil. Network 1 has the pulse timer and network 2 the pulse timer coil. The pulse timer starts on the leading edge of a 0 to 1 transition. The input must remain true for the timer to time to 0. The coil is 1 or true while the timer is timing down, and the coil is 0 when the timer has timed out. Each time the input transitions from 0 to 1, the timer automatically restarts. It is not necessary to assign a reset or output addresses. The time format for all S7 timers is S5T#, followed by the hours, minutes, seconds, and milliseconds. The max time can be 2 hours, 46 minutes, and 30 seconds. The timer's name, T100, also acts as a coil and can be evaluated as a contact. It is not necessary to add an external coil like M250.1, but you can if you like. Let's monitor the block. Highlight network 1. We will energize input 1.6 and leave it true while the timer times to 0. You'll notice that the T100 bit in network 3 follows the timer. Transition input 1.6 to false and then to true again. If the input goes false before the timer times out, the timer will stop timing and the coil goes to 0. Each time the input transitions, the timer automatically restarts. The pulse timer coil in network 2 operates in the same manner. To review, the pulse timer starts on the leading edge of 0 to 1 transition. The input must remain true for the timer to time to 0. The coil is 1 or true while the timer is timing down, and the coil is 0 when the timer is timed out. Each time the input transitions from 0 to 1, the timer automatically restarts. And that concludes this video. In this video, you'll see the extended pulse timer and the extended pulse timer coil. Network 1 has the extended pulse timer and network 2 has the extended pulse timer coil. The extended pulse timer starts on the leading edge of a 0 to 1 transition. The input can be momentary and does not have to remain true for the timer to time to 0. The coil is 1 or true while the timer is timing down, and the coil is 0 when the timer has timed out. Each time the input transitions from 0 to 1, the timer automatically restarts. It is not necessary to assign a reset or output addresses. The time format for all S7 timers is S5T# followed by the hours, minutes, seconds, and milliseconds, up to a max time of 2 hours, 46 minutes, and 30 seconds. The timer's name, T102, also acts as a coil and can be evaluated as a contact. An external coil like M250.2 can be evaluated instead of the T bit if you prefer. Let's monitor the block. Make sure network 1 is highlighted. Let's energize input 1.6 with a momentary input and see the timer time down to 0. The T102 bit in network 3 follows the timer. Each time the input transitions from 0 to 1, while the timer is timing, the timer will restart. When no 0 to 1 transition occurs, the timer will time out. The extended pulse timer coil in network 2 works in the same manner. For a quick recap, the extended pulse timer starts on a 0 to 1 transition. The input can be momentary. The coil is true while the timer is timing down and 0 when the timer has timed out. Each time the input transitions, the timer restarts. And that concludes this video. In this video, you'll see the on-delay and on-delay timer coil. Network 1 has the on-delay timer, and Network 2 the on-delay timer coil. The on-delay timer starts on the leading edge of a 0 to 1 transition. The input must remain true for the timer to time to 0. The coil is 0 or false while the timer is timing down, and the coil is 1 or true when the timer has timed out. Each time the input transitions from 0 to 1, the timer automatically restarts. It is not necessary to assign a reset or output addresses. The time format for all S7 timers is S5T# followed by the hours, minutes, seconds, and milliseconds, up to a maximum time of 2 hours, 46 minutes, and 30 seconds. The timer's name, T104, also acts as a coil and can be evaluated as a contact. You may also add an external coil like M250.3 and evaluate that bit instead of the T bit if you prefer. Let's monitor the block. Make sure that network 1 is highlighted, and we will energize input 1.6 and leave it true until the timer times down to 0. You will notice that the T104 bit in network 3 follows the timer. Transition input 1.6 to false and then to true again. If the input goes false before the timer times out, the timer will stop timing and the coil remains false. If the input transitions from 0 to 1, the timer will restart. The on-delay timer coil in network 2 works the same way. To review, the on-delay timer starts on the leading edge of a 0 to 1 transition. The input must remain true for the timer to time to 0. The coil is 0 or false while the timer is timing down, and the coil is 1 or true when the timer has timed out. Each time the timer transitions from 0 to 1, the timer will restart. And that concludes this video. In this video, you'll see the stored on delay timer and stored on delay timer coil. This timer is called stored on delay because after the timer times out, the coil's value is stored and must be reset for the timer to be used again. Network 1 has the stored on delay timer, Network 2 has the stored on delay timer coil, and Network 3 has a reset for the stored on delay timer coil. The stored on delay timer starts on the leading edge of a 0 to 1 transition. The input can be momentary and does not have to remain true for the timer to time to 0. The coil is 0 or false while the timer is timing down. The coil is 1 or true when the timer has timed out. This is the only S7 timer that must have a reset if it is to be used more than once. The time format for all S7 timers is S5T# followed by the hours, minutes, seconds, and milliseconds up to a maximum time of 2 hours, 46 minutes, and 30 seconds. The timer's name, T106, also acts as a coil and can be evaluated as a contact. You may add an external coil like M250.4 and evaluate that bit instead of the T bit if you prefer. Let's monitor the block. Make sure that network 1 is highlighted. We will energize input 1.6 with a momentary push of the button and start the timer. The T106 bit in network 3 follows the timer. Notice that a transition of the input has no effect on the timer. Let's reset the timer with input 1.5. If a stored on delay timer coil is used, such as timer 107 in network 2, then you must also have a reset bit to reset the timer, such as the one in network 3. Let's start timer T107 with the momentary on I1.7. And reset the timer with input 1.4. To review, the stored on delay timer starts on the leading edge of a 0 to 1 transition. The input can be momentary and does not have to remain true for the timer to time to 0. The coil is 0 or false while the timer is timing down, and the coil is 1 or true when the timer has timed out. This S7 timer must have a reset if it's to be used more than once. And that concludes this video. In this video, you'll see the off-delay timer and off-delay timer coil. Network 1 has the off-delay timer, and Network 2 the off-delay timer coil. The off-delay timer starts on the trailing edge of a 1 to 0 transition. The input is true before the timer starts. When the input transitions from 1 to 0, the timer begins timing down. The input must remain false for the timer to time out. The coil is 1 or true while the timer is timing down, and the coil goes to 0 or false when the timer times out. Each time the input transitions from 1 to 0, the timer automatically restarts. It is not necessary to assign a reset or output addresses. The time format for all S7 timers is S5T#, followed by the hours, minutes, seconds, and milliseconds, up to a max time of 2 hours, 46 minutes, and 30 seconds. The timer's name, T108, also acts as a coil and can be evaluated as a contact. You may also add an external coil like M250.5 and evaluate that bit instead of the T bit if you prefer. Let's monitor the block. Make sure network 1 is highlighted. Input 1.6 is true. We will de-energize the input until the timer times down to 0. You'll also notice that the T108 bit in network 3 follows the timer. If the timer starts timing and the input transitions to 1 and then to 0, the timer will restart. The off-delay coil in network 2 works the same way. To review, the off-delay timer starts on the trailing edge of a 1 to 0 transition. The input is true before the timer starts. When the input transitions from 1 to 0, the timer begins timing down. The input must remain false for the timer to time out. The coil is 1 while the timer is timing, and 0 after the timer times out. And that concludes this video. In this video, you'll see the S7 BCD count-up counter and count-up counter coil. Network 1 has the count-up counter, Network 2 has the count-up counter coil, and Network 3 has a reset for the counter coil. The counter's name, C100, also acts as a coil and can be evaluated as a contact. This only tells, though, if the counter is in use or not. The counter counts up on a 0 to 1 transition of the CU input. The counter's coil is 0 when the count is 0, and is 1 while the counter is counting. The max count value an S7 counter can reach is 999. Assign a reset bit to reset the counter to 0. The PV or preset value contains a C pound followed by a number between 1 and 999. When the input at S transitions from 0 to 1, the preset value is placed at the output, and the counter counts up from that value. The S and PV inputs are generally not used on a count-up counter, but will be shown here for demonstration. The CV output outputs a decimal count value, and the CV_BCD output outputs a BCD value. There is no output signal at a certain count. Use a comparator such as the greater than or equal to comparator in network 4 for this purpose. Let's monitor the block. Make sure network 1 is highlighted. As the CU input, in this example I1.0, transitions from 0 to 1, the counter begins to count up and the C100 bit goes true. If the S input I1.1 goes true, the preset value 200 is transferred to the output and the counter begins to count up from there. If the reset input I1.2 goes true, the counter is reset to 0 and the C100 bit goes false. The count-up coil C101 in network 2 works in a similar fashion, but needs a separate reset such as the one shown in network 3. This concludes the video on S7 count-up counters. In this video, you'll see the S7 BCD countdown counter and countdown counter coil. Network 1 has the countdown counter C102. Network 2 has the set counter coil, which is how you add a preset value to Network 3's countdown counter coil C103. Network 4 has a reset for the counter coil C103. The counter's name, for example C102, can be evaluated as a contact, but this only tells whether the counter is in use or not. The counter must be supplied with the start or preset value. This is done by entering a value between C#1 and C#999 at the preset value input. When the S input, in this example I1.1, transitions from 0 to 1, the preset value is placed at the output. Each time the CD input transitions from 0 to 1, the counter counts down by 1. The counter coil is true while the counter is counting and false when the count is 0. The max countdown from value is 999. A reset can be assigned to reset the counter to 0 if needed. The CV output outputs a decimal count value, and the CV_BCD output outputs a BCD value. This counter does not output a signal at a certain count value. Use a comparator such as the less than or equal to comparator in network 5 for this purpose. Let's monitor the block. Make sure network 1 is highlighted. When the S input I1.1 goes true, the preset value 5 is transferred to the output and the counter goes true. Each time the input I1.0 transitions from 0 to 1, the counter counts down by 1 until it reaches a count of 0. If the reset input I1.2 goes true, the counter is reset to 0 and the C102 bit goes false. In network 2, when input 1.3 goes true, the set counter value coil transfers the value 6 to counter 103. In network 3, each time input 1.4 transitions from 0 to 1, counter 103 will count down by 1 until it reaches 0. In network 4, counter 103 will be reset if input 1.5 goes true. In network 5, the output coil M806.2 is true when the count value is 3 or less and is only shown for demonstration purposes. And that concludes this video. In this video, you'll see the S7 BCD count up and down counter. For this counter, each time the CU input, I1.0, transitions from 0 to 1, the counter will count up. When the CD input, I1.1, transitions from 0 to 1, the counter will count down as long as the output is greater than 0. The counter cannot count down if the output is 0, and the counter does not count negative. When the S input, I1.2, transitions from 0 to 1, the preset value, in this example 50, will be placed at the output. The preset value must be formatted with a C-pound before a number, and the numeric range is between 1 and 999. The counter will then count up or down from the preset value. If the R input, I1.3, transitions from 0 to 1, the counter will be reset. The CV output outputs an integer value, and the CV underscore BCD output outputs a BCD value. Let's monitor the block. Make sure network 1 is highlighted. As the CU input, in this case I1.0, transitions from 0 to 1, the counter counts up. When the CD input, I1.1, transitions from 0 to 1, the counter counts down. When the S input, I1.2, transitions from 0 to 1, the preset value 50 is transferred to the output. The counter then counts up or down from that preset value. When the R input, I1.3, transitions from 0 to 1, the counter is reset. And that concludes this video. Here you will see how to use the IEC pulse timer SFB3. We will do our programming in FC60. FC60 has already been called from OB1. The IEC timers are located in the Standard Library System Function Blocks folder. Drag the pulse timer SFB3 to Network 1. Since this is a system function block, a data block is required. Click on the 3 red question marks. Type the letters DB followed by a data block number that does not exist in the blocks folder of the project. We will make this one DB201 and press the enter key. You'll see a message telling you that the data block does not exist and ask if you want to create one. Click yes. DB201 has been created and placed in the blocks folder. Let's enter I0.0 as the start bit of the timer and press the enter key. The time format for IEC timers is T-pound followed by days, hours, minutes, seconds, and milliseconds. The maximum time value is 24 days, 20 hours, 31 minutes, 23 seconds, and 647 milliseconds. We will make this timer's value T-pound 3 seconds and press the enter key. Let's set the output to energize memory bit 66.0 and press the enter key. Let's store the elapsed time value in memory double word 500. Save the block. Before downloading FC60, we need to be careful to make sure that data block 201 is downloaded first. All system functions and system function blocks are preloaded in the PLC's ROM and do not have to be downloaded. When FC60 gets downloaded, it will call SFB3. SFB3 will, in turn, call for DB201. If DB201 is not in the CPU, the processor will fault. Minimize the programming editor. At SIMATIC Manager, highlight DB201 and download it. Return to the programming editor and download FC60. Turn the monitoring glasses on. Make sure that Network 1 is highlighted because the program monitors from the highlighted network down. When I0.0 is energized, the output M66.0 is true while the timer times down, and goes false when the timer times out. The input does not have to stay true for the timer to time to 0. Let's energize I0.0. This concludes the video on the IEC Pulse Timer System Function Block 3. In this video, you'll see how to add a software jumper to S7 code. Begin by opening a block. Let's open FC21. Select Network 3. Click the glasses to turn monitoring on. Input 1.5 named LL1110 has failed. We do not have another device on hand and need to temporarily bypass the switch so the pump will work. We will do this by adding a software jumper around the input contact. Select the network line ahead of LL1110. Click the branch down button. Add a normally open contact and close the branch. Select the newly added contact. Add the predefined memory bit M0.1, which is an always-on bit. To see how to create an always-on bit, watch the videos on making an always-on and always-off bit. Save the block and download it. Overwrite the existing block in the PLC and monitor the block again. Click the network number so that monitoring starts from the beginning of the network down. Now the switch is bypassed with a software jumper. When we get the replacement part, we'll return to the code and turn monitoring off. To remove the jumper, right-click the contact and delete it. Save the block, download it, and overwrite the existing block. This concludes the video on how to add a software jumper. Shown here is an introduction to some core basic STL commands. Here is a simple AND circuit in ladder and STL. A normally open contact used alone or in series is denoted A for AND, followed by an address. A normally closed contact used alone or in series is denoted AN for AND NOT, followed by an address. The assignment coil is denoted equals for assign, followed by an address. Next is a simple OR circuit. A normally open contact used in parallel with at least one more contact is denoted O for OR, followed by an address. A normally closed contact used in parallel with at least one more contact is denoted ON for OR NOT, followed by an address. Here is an assignment, set, and reset coil. The assignment coil changes with the logic. In other words, if the result of logic is true, the coil is true. And if the result of logic is false, the coil is false. It is denoted with equals. A set coil goes true and stays true until it is reset when the result of logic before it is true. Set is denoted with S, followed by an address. A reset coil goes false and stays false until it is set when the result of logic before it is true. Reset is denoted with R, followed by an address. In the exclusive OR circuit, the output is energized if one input is true or the other input is true, but not both inputs are true. To read this network in STL, it would sound like this: AND I3.5 and not I3.6, or AND not I3.5 and I3.6 equals Q10.5. In STL, the exclusive OR can also be written as X I3.5, X I3.6 equals Q10.5. The CPU knows to perform the exclusive OR function when it reads the X command. However, there is no equivalent ladder logic, so the code will not translate to LAD. A positive edge pulse coil is denoted FP in STL and must be followed by a unique memory address. An easy way to remember the mnemonic is think fire positive plus the address. A negative edge pulse coil is denoted FN in STL and must be followed by a unique memory address. An easy way to remember this mnemonic is think fire negative plus the address. When moving, which is actually copying data into a location, the data must first be loaded, which then goes into accumulator 1. The data is then transferred to the desired location. In STL, this network would read load 50, transfer to memory word 120. The no op 0 means there is no operation on the enable out or ENO side of the block. The STL code will work fine without this command, but will not translate to LAD. In this video, you have seen some core basic STL commands. Watch the other STL videos for deeper travels into STL.
In this video, you will see how to program the IEC on-delay timer. The IEC on-delay timer, System Function Block 4, is located in the folder Standard Library and subfolder System Function Blocks. Let's drag SFB4 onto the network. When a function block or system function block is used, you must assign a data block. Click on the 3 red question marks. Type in DB for data block, followed by a numeric value. Make sure the data block value has not been used in your blocks folder. We will assign data block 202 and press the Enter key. The programming editor will check the blocks folder, see that the block does not exist, and ask you if you want to generate it. Click Yes. Assign a bit to the in parameter. We will assign I0.1 and press the Enter key. To the PT input, assign a time value with the format T pound, followed by days, hours, minutes, seconds, and milliseconds. You can highlight the SFB block and press F1 for more help. Let's enter the value T pound 3S. We will assign memory bit 99.1 as the output to be energized by the timer. Assign a memory double word such as MD400 to the ET or elapsed time output. Save the block. Minimize the programming editor to return to SIMATIC Manager. We will now download data block 202 that was created by the editor. Don't forget to download the data block first or the CPU will fault. Click the download button. Now let's return to the programming editor and download the block FC60. FC60 is already being called from OB1. Turn on monitoring. Make sure that network 1 is highlighted since the program monitors from the highlighted network down. When I0.1 transitions to true, the timer begins to time. After the delay time, that is, when the timer times out, output memory bit 99.1 is energized. This concludes the video on using the IEC on-delay timer, System Function Block 4.
In this video, you will see how to change a timer value for both SIMATIC timers and IEC timers in an online block and how to save the block to your offline project. FC5 has some timers in the block, so let's open it. You can tell whether the block you're looking at is the offline project block or online PLC block at any time by clicking on the Error tab. This block is the offline project block. Clicking the eyeglasses for monitoring does two things. One is it lets you monitor the block. But secondly, if the offline project block does not match the online PLC block, you will get a pop-up message. Because the block is being monitored and there was no message saying that the blocks didn't match, we know the online and offline blocks are identical. Let's now open the online PLC block for some testing. Click on the eyeglasses again to turn monitoring off. Click the Online-Offline toggle button. You'll see a message asking you if you want to close the block, in this case the offline block, and open its partner, the online block. Click Yes to open the online block. Notice that the Error tab now shows that you are looking at the online block. Click the glasses to monitor. The first timer is a SIMATIC on-delay timer, which was pulled from the Timers folder in the catalog. All SIMATIC timers have the time format S5T#, followed by the number of hours, minutes, seconds, and milliseconds. The maximum time for one of these timers is 2 hours, 46 minutes, and 30 seconds. Currently, this time is set for S5T#, 25 seconds. It has been determined that this is not quite long enough for our process. Let's change the value to S5T#, 26 seconds and test it. First, download the block, then highlight Network 1 because monitoring takes place from the highlighted network down. The full timing out of the timer is not shown. However, 26 seconds is still not long enough. Let's change the time to 30 seconds and download the block. Make sure Network 1 is highlighted and test the block. Again, the timing down is not shown. This value worked, so now what we want to do is save the online block to the offline folder where the blocks will again match. Turn off monitoring. Click the Save button. Now the online block in the PLC and the offline block in the project are identical. Now let's have a look at SFB4, the IEC on-delay timer in Network 3. Two things stand out right away. One is that this timer has a data block attached to it because the called block is a system function block. Secondly, the time input is different. The IEC timer input is just T# followed by the days, hours, minutes, seconds, and milliseconds up to a value of 24 days, 20 hours, 31 minutes, 23 seconds, and 647 milliseconds. Data block values in the PLC of a running process will almost always be different than data block values in the offline project. Let's see an example. Minimize the programming editor. Right-click on the Blocks folder and choose Compare Blocks. The default is to compare online to offline blocks. Click the Compare button. Here you see that the download timestamps are identical, but the actual values are different in the PLC. That's because the process is constantly writing new values to the data block. In this case, we only want to change the timer's value, so the data block will not be a problem. Close the Compare window. Close the Comparison tool. Back in the programming block, turn the monitoring glasses on. Notice that we are still in the online block of the PLC. Select the IEC timer's input value. Let's change the value from 9 seconds to 8 seconds. Download the block. Make sure that Network 3 is selected and test by energizing input I1.4. The timer's full countdown is not shown. Let's select the time value again. Change the value to 6 seconds. Download the block. Highlight Network 3 and test the timer again. While the full time down is not shown, this value works for what we are trying to accomplish. So turn the monitoring glasses off and save the block to the project. The online and offline block match again. In Review, you can open a block that has a timer and switch to the online block. Test time values until you find the one that works best. Then turn the glasses off and save the block, which puts it in the project so that the online and offline blocks match. For more information on timers, watch the videos on SIMATIC timers and IEC timers. You can also learn more about block comparisons and examining differences in blocks in the video Compare Online and Offline Blocks. And that concludes this video. Here is where to find SIMATIC help when programming in STL. The first resource is the documentation that's installed with SIMATIC Manager. Click the Start button. If using Windows 7, click on All Programs. Locate and click on the Siemens Automation folder. Then find the SIMATIC category. Next, click on Documentation. Note that only installed languages will display. We will choose English. Locate and open the manual called Step 7 Statement List for S7 300 and 400. This manual does a nice job of covering statement list programming. We'll take a quick look at the first few pages. The first two pages are an overview of Boolean instructions, followed by detailed pages of the AND statement, the AND NOT statement, the OR statement, the OR NOT statement, and so forth. Let's close the manuals window. The second reference is a list that shows all statement list commands. To find it, first double-click a block to open the programming editor. From the programming editor, click the Help menu. Choose Help on STL. The first topic in the list is Overview of all STL instructions. Click the Open button. You can choose to sort the instructions by English or German mnemonics. We will sort by English mnemonics. Then click Display. Here is the list. We'll take a quick tour down the instruction set. Click a topic link, such as exclusive OR. You will find detailed information about the topic. Let's close the Help window. The final reference is inside the STL code itself. Click next to a command and press the F1 key. Detailed help about the command will appear. You have seen that you can get STL help from the manual installed with SIMATIC software, the programming editor's help on STL topic, and by placing the mouse cursor next to a code instruction and pressing F1. This concludes the video on STL help. In this video, see how to set the CPU to test mode or process mode. For newer CPUs, the test or operation mode is set from the programming editor. To begin, select the Debug menu and choose Operation. The default is Process Operation, which limits the amount that scan time can be increased by monitoring functions and guarantees the minimum scan cycle time during monitoring and debugging operations. Debugging by using breakpoints is not possible, and monitor with call-up path for multi-instance calls is also not possible in process mode. For these, you must select Test Operation. Test Operation allows you to put the CPU in hold mode, such as for loop testing with breakpoints, and to expand monitoring time for operations such as call-up path for multi-instance calls. When you've made your selection, click OK. If you are using an older CPU, these choices are made in the CPU properties of the hardware configuration. Keep watching to see an example. I'm going to open up a project that has an older CPU in it. Open the Hardware Configuration Editor and double-click the CPU to open its properties. Click on the Protection tab. For newer CPUs, the mode section is not shown here, but for older CPUs, this is where the setting is made, and note that test mode is the default. If you change the mode, you will have to download the hardware configuration again. You've seen that for newer CPUs, the default is process mode and changes are made in the programming editor with no download. For older CPUs, the default is test mode and the selection is made in the CPU's properties of the hardware configuration. A download is then required. And that concludes this video.